Well, hello, folks. This week we have a thriller for you. um, so, at this point in this course, we are kind of making a shift. For the most part, we have been dealing with the first half of statistics, which we typically simply refer to as descriptive statistics. That is, we've primarily focused on how do we describe our distributions of numbers or scores or our samples or populations. This week, we're actually now pivoting to really the second part of statistics, something that's typically called inferential statistics. Now, this word inferential is just a fancy word for hypothesis. A hypothesis is an inference. So, what we're really pivoting to is now talking about how do we use statistics to test hypotheses. And so for this reason, I kind of did something strange. I've asked you to kind of look at portions of chapter 8 with the focus on chapter 9. And so what I'm going to do in this lecture is to kind of give you a quick overview of chapter 8. I should say that if you find that you're understanding what I'm talking about, then you might be cool with just sort of beginning with chapter 9. On the other hand, if this part is sort of confusing to you, then you might actually want to go back and give a more thorough read to chapter 8, particularly the parts around what I'm talking about, because I'm going to be talking about basically how does statistics test a hypothesis. And so that's what's covered in chapter 8. What I'm basically skipping is how that's applied to testing hypotheses around proportions, which is something that we're really not focusing on. I really want to focus more on how to test hypotheses having to do with means, which sort of picks up chapter 9. But as far as this book is concerned, it really sort of presents the information around hypothesis testing in chapter 8. So that's where we're beginning. Okay? So in terms of chapter 8, one of the things that's sort of introduced to you is the important distinction between something called the null and alternative hypothesis. For the most part, generally when we use the term hypotheses, we're kind of using that very generically. And the real name, or I should say the full name of that's actually called the alternative hypothesis. Something that's normally always implicit when we make hypotheses is something called the null hypothesis. And you're going to be this is going to be a little bit of a brain twister, but you're going to kind of learn that primarily when we are testing hypotheses, we're actually more focused on this thing called the null than we are on our alternative hypothesis. So let's begin with what the null is. Typically, it's printed as sort of an H sub O. We typically will call that H naught, or most people, when they look at that, they see that as the null hypothesis, right? So when you see this sort of H sub O, once again, it's typically called H naught, you'll know that's the null hypothesis. And so what does the null hypothesis basically say? Well, it basically says that nothing is going on, right? And so, you know, it's sort of it's sort of akin to saying that, hey, what we see here is just the status quo. There's nothing special going on. There's no cheating, no surprises. There's been no change. There's no effect. Okay, so that last term will be the one you'll relate to most. That is, the null hypothesis basically says there's no effect. Now, keep in mind, normally when we're making hypotheses, we are normally trying to argue that there is an effect. So notice that the null hypothesis normally says the opposite of what we're saying. It says that there's no effect. Okay. Typically, the hypothesis that we're interested in looks like this sort of HA, and this is the alternative hypothesis. That's its full name. It's called the alternative because it's basically the alternative to the null. And once again, what you're going to find kind of brain teasing in this chapter is just how much statistics, particularly inferential statistics, are really shaped around the null rather than the alternative hypothesis. So, the alternative hypothesis, this is what we hope, or probably said a little bit better, this is what we guess is true, right? So when we say that a hypothesis is an educated guess, right, we're typically, once again, talking about the alternative hypothesis. Okay, and so one important thing to note, and that is that whenever we are doing inferential statistics, in other words, whenever we're testing hypotheses, we are generally talking about the population statistic, right? In this chapter, it's focused on proportions. That's why the slide says proportions, but population, whatever, right? Proportions or means. But the point is that we're always interested in talking about the population, not necessarily just our sample, right? We're not, we're not just sort of making a hypothesis about the sample that we're using because our sample is limited, right? If I get my sample in St. Louis, then, I'm not just interested in people in St. Louis, I'm interested in people around the world. So I'm interested in the population of people, not just the people that are in St. Louis, okay? So one of the things then that's introduced in this chapter is something called the level of significance, okay? And the level of significance typically reflected here as alpha, that little A thing that you see, is the probability of rejecting the null when the null is true. Okay, so I want you to think about that. It's the probability of rejecting the null. Now remember, the null says there's no effect. Okay, when that null is true. So if I were to say it differently, I'd say this is the probability of you suggesting that there's an effect when there's no effect. So basically, the probability of guessing wrong is what we're talking about. And that's what this alpha is. And that's essentially what the level of significance is. It's the probability of guessing wrong, right? We say there's an effect, but all along there is no effect. Okay, so think about something like concluding that the coin tossing is not fair when it is fair. Okay, thinking about things like saying that the defendant is guilty, but he did not commit the crime. Okay, or concluding that a person has psychic abilities, right, when they're really just guessing. All of these would be cases where we would reject the null, because remember, the null is basically saying nothing is going on here, right? There's nothing happening with respect to the coin tossing, right? The defendant did not commit the crime, and the person doesn't have psychic abilities. That's essentially what the null would say. But if we concluded these things, right, we would be rejecting that null, even though that null is not true. Okay? And so one of the things that you have to decide in science is how much of a risk that you're willing to take, right? Every scientific conclusion faces the possibility of something like this, right? If we say that, as a result of our experiment, that a certain drug worked, right, and the drug doesn't work, right, we are potentially having the same issue here. If we say that some particular effect in a laboratory worked and it doesn't work, we have that same kind of problem. So any scientific conclusion always has the possibility of not being true. And so at some point we have to kind of decide in science, okay, where are we going to draw the line? What's going to be our quote-unquote level of significance? And that's really kind of the threshold. Where do we draw the line for how much risk we're willing to take? And that's really what we mean by this alpha. And so there are some typical levels of significance in science. Since the level of significance is the probability of making an error, right? We all agree it should be small, right? So there's general agreement that our probabilities of making errors should be small. Where it tends to vary has to do with what we're doing. So the typical alpha level is what's called the 0.05, which basically, you can kind of think of it as a 5% probability of making an error. Now, this is not something that's calculated. It's just sort of a given, right? It's like pi equals 3.14. It's something that was decided upon long before any of us were born. Scientists said, okay, that's going to be our level. But recognizing that there are times in which you actually need a more conservative threshold. So there are times in which some people say, you know what, 0.05 is not going to do. We want a more conservative threshold, so we're going to go to 0.01, which means that we're only willing to accept a 1% error in this case. And then there are times in which some people say, you know what, maybe 0.05 is too conservative, and we want something a little bit more liberal. And so there may be times in which the threshold might be lowered to say a 10% chance of making an error. Once again, unless you have a good reason for either restricting it more to a 1% or loosening the range at a 10%, typically we're going to choose the 0.05. I will tell you that in this class, everything else that you're going to face is going to pretty much be at this 0.05 unless you are asked to choose a different alpha level. So 0.05 is the default for the most part. Okay. And we'll talk a little bit more about how this sort of significance thing comes into play, but you'll discover that anytime you run statistics, you're going to be given a probability of that statistic, okay? And we'll generally be looking at that probability and comparing it to these thresholds, right? And such that only when we find the probability of a statistic to be, say, less than 0.05 would we say it's significant, okay? And that's because it's falling underneath our threshold, okay? If we use that 0.01, for example, it would have to even be smaller than 0.01. Okay, if we use the 0.10, that means that if it's at least under that, and so in some cases, if it were like 0.09, that would actually not be good enough for our 0.05 threshold, but that would work for the 0.10 threshold. So we'll always be sort of looking at the probability that we get for a statistic and comparing it to these sort of set alpha levels. But by default, 0.05. Okay, let's move on and talk about the test statistic then. Okay. So a test statistic tells us how unlikely that the sample proportion could have happened by random chance had the null hypothesis been true. Okay, we need to digest that a little bit. It's telling us how unlikely that the sample statistic, once again, doesn't have to be a proportion, it can be a mean. So it tells us how unlikely that that sample statistic could have happened by random chance had the null hypothesis been true. Hopefully you'll see the connection to what I'm saying here versus what I said a couple slides ago, right? Because essentially that's what we're trying to figure out. We're trying to figure out if that null is true or not. And we're trying to figure out what the likelihood of that being true or not true is. If the null hypothesis is true, then the test statistic should be close to zero. In other words, if there really is no effect, then the test statistic should be close to zero because that would basically be the indicator of no effect. Okay, so therefore, the farther the test statistic is from zero, the more the null hypothesis is discredited. So the value that you get when you run your test statistic is very much connected to this idea of the probability that you get. You'll generally see that the larger that test statistic is, the more likely your probability will be small, right? Fall up under that threshold. And the smaller your test statistic, the more likely your probability will be high. Okay. All right. So what I've been hinting at then is this thing called the p-value, right? And this is the probability statistic. And so once again, assuming that the null hypothesis is true, the p-value is the probability that if the experiment were repeated, you would get a test statistic as extreme as or more extreme than the one you actually got. A small p-value suggests that a surprising outcome has occurred and discredits the null hypothesis. Once again, I hope you see that I'm kind of saying the same thing over and over again. Okay, so if this wording kind of throws you off, don't let it, because I'm basically being redundant. So this is just another way of talking about the fact that this p-value really is an indication, right, that the probability of making a mistake is small. Right? So the smaller the p-value, the smaller the likelihood of making a mistake. What mistake? The mistake of rejecting that null when the null is really true. Okay? So unlike other places where you think that larger numbers might be better, in statistics, at least when it comes to the p-value, smaller p-values are better, right? Because they suggest a smaller probability of making a mistake. Okay, so one more thing, well, actually probably a couple more things from chapter 8. is the idea of the steps to hypothesis testing. One of the cool things about this is that these 4 steps are true for every inferential statistical